All right, so my name's Saul, like the sleazy lawyer from Breaking Bad, if you watch that show. And I'm going to be talking today about some Clojure tools for symbolic AI. These tools were created by a friend of mine, Dr. Simon Lynch, and I had to use them as part of finishing up my university degree in final year. And I've used them a few times since then, and I've gone on to help develop and contribute to them. So which tool specifically? Well, first of all, we're going to be talking about a pattern matcher, a fully featured symbolic pattern matcher for Clojure, which was ported over from Common Lisp, would you believe it? This being a symbolic AI talk. And in a nutshell, you can flexibly iterate over collections of structured data and just pull out the information that you're interested in. So for example, if we've got a set of data about a whole bunch of different foods, we need to know the name of every red vegetable. The symbolic pattern matcher can help us out there. And here's a little bit of an example. Sorry if it's a little bit small to read. No, actually, it's huge, from my perspective anyway. So first of all, we're pulling out every vegetable. We're using the little question mark form here, which is a matcher variable. That creates a variable in kind of a behind-the-scenes pseudo namespace, separate from the Clojure namespace or Clojure namespace concept that we're all used to, and it binds the middle symbol here to the name f, and then we use the question mark function at the end to pull that f back out of that pseudo namespace. So M4 will do that. M4 asterisk or M4 star or M4 many, whatever you want to call it, is going to do that with multiple tuples. So now we can find the name of every red vegetable. Also, we're going to be talking very briefly about operator search mechanism, which is kind of a partially optimized breadth-first search mechanism for applying strips-style operators. Anyone heard of strips? Fantastic. I'm in the right place then. All right, so strips, Stanford Research Institute problem solver. It's kind of a bit of a dated, a bit of a classic, but also a very robust way of creating a set of operators that you can use to interact with a world state. So I'm going to have a little bit of a demo for you coming up in a second. First of all, I'm going to give you an example. So we need to move a keg of beer into the living room. We're having a really sick party, and we need to move a whole keg into the living room. Things are getting a bit wild, but right now we're in the garage, and the beer is in the kitchen under the celery. So under the assumption that we can't move the keg of beer without first moving the celery, because you don't want to be bringing a packet of celery into the living room along with your cool keg of beer, what do we need to do? And to us as humans, that's very intuitive. We can just say, oh, well, we need to move the celery, we need to go to the kitchen. Okay, go to the kitchen, then move the celery. Excuse me, keep your seats. We need to go to the kitchen, move the celery, pick up the keg, move into the living room, and drop the keg gently. But yes, how does a machine do that? How do we get a machine to do this planning for us? So it's example time. So if the stars align, I should be able to show you a quick demo now. Are you seeing what I'm seeing? Yes, you are. Wonderful. So on the Cognescence GitHub, no relation to our wonderful host Cognitect. Cognescence is the name that our organization has. We have this shrep thing, the shrep client and a shrep server. So the shrep client is in NetLogo. Who's used NetLogo before? Couple of hands. Nice one. For the purposes of this demo, we're going to be just using NetLogo as kind of the UI. It's kind of a visualization of what is happening in the world state in the Clojure program. And then we've got this Clojure thing server side. So let's give it a command. Let's say make a red box and put it on top of B1, which is our blue box. So you can see we get B2, which is a red box, and we just pop that on top of our blue box. Now we're going to make a yellow box, and we're going to put it somewhere else. We're going to put that on S7, stack 7. And here comes our little winch, dropping our yellow box onto S7. So this is quite a simple case. But what if we need to move B1 now? what if we want to Windows, thank you very much. They never did quite get the whole command line thing down, did they? All right, so let's start that again. We want to put B1 on B3, which is our yellow box. And there we go. So our planning mechanism has worked out that B2 is in the way right now. So we need to move B2, put it somewhere else, and now, finally, we can realize our goal of having B1 on top of B3. Spoilers. Okay, so how did that work? Let's get back to the presentation here. Once again, fingers crossed. Nice. So, how did that work? Well, we start off at the very low level with a legal move generator. A legal move generator is just a function that takes our initial state and produces a set of successor states. So we do one move, essentially. We apply one operation. So yeah, there's my little diagram of an LMG, of a legal move generator and its structure. We start off with our initial state S0, and we produce S1, S2, and S3 from applying each of our 3 applicable operations. So let's play Countdown. Countdown is a simple game that we played in my maths class in upper school. And we need to get from one number to another number using only a limited number of mathematical operations. There are some examples. I loved it. I loved Countdown. Actually, I didn't love Countdown very much. I hated it. As a 14-year-old, I didn't enjoy using my brain very much. Thankfully, that's changed, sort of. All right, so now let's capture this in an LMG. So we define our LMG function that takes a state n. In this case, n is a simple integer. And we apply an operation, or our 3 relevant operations to n, and return those in a vector. So if we do LMG 10, then we're going, excuse me, that seems like, yeah, LMG 10 is going to give us 13, 20, and 3 back. It's going to apply each operation to 10 and hand it back to us in the collection. So let's just run a breadth-first search on the resulting tree. Now, this breadth search implementation is available. It is on the Cognizance GitHub. But it is literally just a few lines. It's a breadth-first search that runs along the tree of states generated by this legal move generator and gives us a solution. So we add 3, multiply by 2, and add 3. And we get from our initial number to the number we're trying to get to. We get from 5 to 35. So let's get a step more complex. Let's apply, or let's declare, let's create, formulate, and apply a set of strips-style operators to our LMG. So rather than hard-coding the operators directly into the LMG, let's pass in a set of operators instead. This will create our state transition graph, and we can search that state transition graph for a state that satisfies our goal. So strips, Stanford Research Institute problem solver, like I mentioned. There's a paper on this, quite an old paper from the 70s, but still a very, very good read. We have a set of preconditions. Now, not every operator is going to be applicable in every case. If our celery is on top of our keg of beer, we can't move the keg of beer. In my mind, anyway. So our preconditions are our agent needs to be an agent, meaning it needs to be animated. We can't have the keg of beer take the celery off itself. We need to have a manipulable object in order to pick it up. We need to be at the same place as our object. So our agent needs to be in the same place as our keg of beer, and the agent's hands need to be empty. Holds agent nil. When we perform this operation, we're going to add a tuple to our world state, we're going to add a fact, and then we're going to take 2 facts away. We're going to add the object in the agent's hands, and we're going to remove the object from wherever it was before, and remove the fact, somewhat counterintuitively, that our agent is holding nothing. That might seem a bit strange at first, but what we're trying to do is maintain a world state, containing every fact that we're going to need to know. And the fact that our agent doesn't have anything in its hands right now is relevant to the application of our operator, so we're going to have to remove it. Okay, back to the REPL. So we're going to run the operator search mechanism now that underlies the example with the winch that I just showed you. And hopefully shed some light as to how it worked. So, please tell me I've got my other REPL open. Wonderful. Okay, so let's load in an example. This example, by the way, contains the world state with a book on a bench, and we're going to be moving that book to a table. So load file, if my memory serves, examples. There we go. So ops search. I can never remember the order of the parameters for this function. There we go. Is this a bit small? Yeah. Okay, so as you can see, our goal state is the book being on the bench. In the initial state, it's on the table, and this is a gigantic printout of each step we've taken to get from our initial state to our goal state. So a little TLDR is at the bottom here. Grasp book, move to bench, drop book. Excuse me. Okay, so closely, obviously the matcher, which is the main reason I'm here to talk to you all today, plays a very integral part in that operator search mechanism because it allows our operators to be general. So we can use these matcher variables to create general purpose operators. We would not need a separate operator for moving to the kitchen and picking up a keg of beer specifically. It doesn't matter if our name is Frank and we're picking up a keg of beer in the kitchen, or whether our name's Hannah and we're picking up our laptop in the library. It doesn't matter. We can write one operation or one operator, and we can apply that in too many different world states to achieve a whole variety of different goal states. Closely related then is inference. So this is another example using the matcher, really showcasing what it's capable of. Excuse me. I should have taken my allergy tablet this morning, I think, rather than sniff into the microphone at you all. Okay, so if Pierre is Jack's father and Jack is Mary's father, we know that Pierre is Mary's grandfather. But we don't have that fact in our world state right off the bat. We need to do some inference. So what we can do is define this grandparent rule. So if A is the parent of B and B is the parent of C, we can safely infer that A is the grandparent of C. We can then add this to our fact base. And maybe the fact that we have some grandparents in our fact base now is going to allow us to infer additional information about our world. So we can repeatedly apply this process of inference until we stop inferring new facts. And that can be extremely useful. And I'll give kind of an example, real-world scenario a little bit later on in the presentation. So the matcher, or the matcher library, we've just called it the matcher. Suggestions for call names are welcome from anyone here. We define a matcher function using this def match macro. So we declare a compile rule matcher function, and we pass in a rule with an ID and a set of antecedents and a set of consequence. So it's essentially a set of causes and a set of effects. So using that syntax, we can turn these tuples of rule, ID, antecedents, consequence into a map which we can more cleanly work with. So let's apply our rule. So we have our set of family data, and we have our apply rule function, and we're going to apply the compiled version of our grandparent rule to this set of facts. I believe the compile function was, yes, the compile rule function's back here. So we're going to compile that grandparent rule, and we're going to apply it to our family data. And what we get out at the end is that Ellen is Tom's grandparent and Rob is Sam's grandparent. And this is, just by looking at that sort of as a human, at least for me, my head would start to spin. There are so many parent-child relationships there, but we can very effectively infer additional information in an automated way from what we've got here already. So let's talk about how we might bring this theory into practice. Hopefully that's readable. So say we've got our phone's voice assistant, Siri, Alexa, Google, whatever you call your phone, Siri, Alexa, Google. You say, hey, Google, or whatever, let my grandparents know it's my niece's birthday on the 25th. That goes through a speech-to-text engine, and we do some basic information extraction on that to arrive at the state in this orange box here. So we need to inform the grandparents of the user that it's the user's niece's birthday on the 25th. So there's actually a project that Cognizance has in the works that I'm taking part in porting a library called LKit, which is written in Common Lisp, over to Clojure. And hopefully that will provide sort of the missing piece of the puzzle here, going from this free text to this set of information here. So that's LKit. I've used it before. It's pretty cool. It's for natural language parsing, and it's not machine learning based. It's sort of a AI based thing. Sort of all sort of cold hard functions in there. So not as cool as the machine learning stuff, in my opinion, but still a really interesting tool to add to your toolkit. So we'll keep you up to date on all that. Anyway, to not get sidetracked for a second here, the grandparents of the user might not currently be known. We might be pulling these parent-child relationships from the Facebook API, for example. And to my knowledge, that's certainly possible. It seems like something that should be possible with Facebook's API. Find the parents of this person. And if you have Facebook integration turned on your Google smartphone or your iPhone or whatever you use, I can totally see it integrating with that service in that way. So what we need to do is gather the family information that we can, because you might not have your grandma on Facebook, and we need to infer as much as possible. So we infer from the parental relationships who the user's grandparents are. From there, we formulate our goal, which is that the grandparents are aware of the niece's birthday. And we use a set of operators that we might have coded into our AI to look up the grandparent's phone number and send an SMS. And that realizes the goal of the grandparents being aware of the niece's birthday, at least from the perspective of the system. So then we carry out that plan. We have something that we can action in an automated way that we've also planned in an automated way from limited information that we had initially. So yes, the code is on, or the releases are on Clojure. Everything's on Lineagon, and GitHub, the Cognizance GitHub organization, is up there to, it's got I think most of our Clojure code up there right now, but more is certainly on the way. And obviously feel free to comment, criticize, PR if you have a spare moment of an evening. And this talk does have a companion paper. Now, there's a whole lot more detail in this paper than I've covered today. I anticipate you guys probably have some questions. I'm very happy to take those. And it really does document the API quite extensively, certainly to a deeper level of knowledge than I myself possess around the matcha in particular right now. So well worth a read. It's up on cognizance.co.uk /Euroclojure 2017. That was not a brilliant choice of font there, but you know, that's PowerPoint for you. So I guess that's everything I have for you guys today. Are there any questions?